So finding the equation of the inverse, finding graphic inverse equations. To find the equation of inverses, there are 3 steps to follow. To find the equation of the inverse, you're going to switch x and y in the equation, solve for y using inverse operations, and then write the equation using inverse function notation. Okay, does it sound terrible? No, not at all. So here we have y equals 4x plus 8. So following those 3 steps to find our solution, we're going to switch x and y. So we're literally switching the x and y location. And that's going to leave us with x equals 4y plus 8. Any problems with step 1? Okay. Step 2 tells us to use inverse operations to solve. Inverse operations means that instead of adding, I subtract. Instead of multiplying, I divide, right? And vice versa. So I'm going to subtract 8 from both sides. And that leaves me with x minus 8 equals 4y. I'm going to divide by 4. When you multiply and divide, it affects all terms, okay? So I'm not going to just divide 1. I'm going to divide all terms by 4. So I'm left with 1/4 x minus 2 equals y. Okay? The last step is to write it in inverse notation. So writing it in inverse notation literally means I'm now writing y inverse equals 1/4 x plus 2. And that's your inverse. Oh, it's not plus 2, it is minus 2. Erase the wrong line. All right, questions, comments, concerns?
How did 1 is 4 become an x? 1/4x?
This right here?
Yeah.
X4, there's a invisible 1. And multiplication, you either can keep it together or separate it.
So there's always a 1 by the x.
There's always I call him Casper, the friendly one. Because it can be there if it needs to, and it can disappear if it doesn't. Questions about number 1? Okay. Number 2. So number 2, the only difference here is instead of starting off as y equals, we start as f of x. That's an easy fix. Y equals. So now we're y equals. I'm going to switch the place of my x and my y. And that's going to lead me to x equals 7 minus 5y. Use my inverse operations. Subtract 7 because it's positive. And I'm left with x minus 7 equals negative 5y. I'm going to divide by negative 5. And again, I'm dividing all terms by negative 5. And that's going to leave me with negative x fifth plus 7 fifths equals y. And the reason why it's plus is because a negative divided by a negative is a positive. Last step is to write it in inverse notation. Now, because they share a denominator, notice how my denominators are the same. I have a couple options of writing the answer. So option 1, I can write it as inverse of how it is, negative x over 5 plus 7 fifths. Option 2, I can write it as equals negative x plus 7 over 5. Either one is acceptable. And again, why can I do that? Because they have a common denominator, right? How do we feel? Good? It's not terrible, right? All right. Example 3. Now we're in a different format, but it's still a linear equation, right? And how do I know it's linear?
An x plus b.
Because it has to do with the x, because the power of the x is still just 1, right? It's just still the power of x. So this is still linear, it's just written in point slope notation. Okay, it's not written in slope intercept like the other two examples. But it doesn't change anything. Again, f of x is just y. And I'm going to switch the places. So now I'm working with x equals 5/9 times y minus 32. Does anyone remember the inverse operation for multiplying by a fraction? We don't have to. We can get rid of the fraction first. But does anyone remember the inverse operations to get rid of a fraction? So to get rid of a fraction, the inverse operation is you multiply by its reciprocal. So you multiply by its reciprocal. And reciprocal means that I is a fancy way of saying flip the fraction. So instead of 5/9, I'm going to multiply by 9/5. And what I do to one side, I do to the other side. Notice how it kindly crosses out. And I'm left with 9/5 x equals y minus 32. So again, what's the inverse operation for a fraction? We all now know. Multiply by reciprocal. Was it terrible? Not at all. All right, so I have subtracting 32. Inverse operation is to add 32. So we have 9/5 x plus 32 equals y. Final step is to write it in inverse notation. So my answer is actually inverse of f equals 9/5 x plus 32. Okay, feeling okay? Day 1 of actually computing something in this class? All right, example 4. We're now working with, instead of linear, what do we have? Quadratic. We're now working with quadratic because our power is 2. That 2 lets me know that we're working with a quadratic. Pretend that's an arrow. All right. Well, we learned about quadratics. What did we say the inverse function for a quadratic was? Anyone? I know it was last week. Well, the inverse function of a quadratic is a square root function. Okay? The inverse of this is square root. Okay? So we're going to be using square root to cancel out the quadratic. Does that make sense? Because that's its inverse function. All right? So following our steps, we're going to switch our x and y. And now I'm working with x equals 2y squared minus 6. Step 1 completed. Step 2, use inverse operations to solve for y. So I'm going to add 6. And what I do to one side, I do the other. So I have x plus 6 equals 2y squared. I have to cancel out my Multiplication. So I'm going to divide all terms by 2. And I'm left with x over 2 plus 3 equals y squared. How do we feel? Okay. The only point of change is here.
Why do you use city? Did we use it wrong?
We did use the 2.
No, I'm talking about why.
We're about to.
Oh,
So the difference here is now our y is still not by itself. It has that pesky little 2 hanging around. Well, that quadratic is what we're getting rid of. And what did we say the inverse of the quadratic was? The square root. So in order to get rid of the 2, I'm going to take the square root. And what I do to one side, I have to do to the other side. When you take the square root of a function or a number in general, it's going to create a positive and negative solution. So we put that plus or minus in front. And our y is free. This cancels out that 2. Okay? And think about the reason why I put the plus or minus. If I was to take the square root of 4, my solution could either be negative 2 or positive 2, because a negative times a negative is a positive. All right. Now, last step is to write it in inverse notation. So y inverse equals plus or minus square root of x over 2 plus 3. All right, so let's recap from this. What we have to do. So we notice that we're no longer dealing with a linear. We're dealing with quadratic. The inverse of a quadratic function is square root. Okay, so keeping that in mind, then we prepared ourselves. We switched our x and y, and we got here. We used our inverse operations all the way down. The inverse operation of a square is a square root. We took the square root. When you take the square root, the result is going to be a positive and a negative of the solution. And then we wrote it in inverse notation. Easy? Still with me? Cool, cool, cool. All right. So on 5 here, we have the square root. So obviously, the opposite of the square root is going to be the square, right? So if I'm going from square root, then I'm going to have to square. So first step is I'm going to make u into a y, and I'm going to switch my x and my y. So I'm left with x equals the square root of y squared plus 5. Okay, I need to get rid of the square root. So to get rid of the square root, I'm going to square the entire thing. And what I do to one side, I have to do to the other. Squaring the square root cancels it out. So now I'm left with x squared equals, and this is now no more, y squared plus 5. Now what else do I need to do to get y by itself? What's next? You can't do this by myself, so we're going to subtract 5. Good job, John. We're going to subtract the 5, and we get x squared minus 5 equals y squared. And now, Anna, since y is left with just a square, we're going to take the square root. So we're going to take the square root, and what I do to one side, I have to do to the other side. The square root is going to cancel out my square, and it's going to produce a positive and a negative. Square root of x squared minus 5. Final step is to write it in inverse notation. So in inverse notation, I have f inverse of x equals plus or minus the square root of x squared minus 5. Plus or minus the square root of x squared minus 5. Questions about example 5?
Yes.
Yes.
Why do we not take out the x at the end? Because it's it has a square root, so it would.
What do you mean take the x out of the end?
Well, like because it's squared, so it would.
Because it's combined is not by itself.
Oh.
So it's connected to this 5. So when something is connected through addition and subtraction, they cannot be separated. So you can't simplify just one term without having to simplify the other.
Okay.
Good question. All right. Now, what is the parent function for this guy?
Rational.
Rational. Good job, Benja. It is rational. Okay? Rational means that you are dividing by x, right? What's the opposite of dividing by x? Multiply. So my inverse is going to be canceled out by multiplying. I'm going to multiply the x. I don't know why I wrote purple on purple. I really don't. It's too late. It's already happened. All right, so same steps we're going to follow. Doesn't matter that it's written in fuck. I'm going to just write it as a y. I'm switching the x and the y. So we're working with x equals negative 5 over y. Okay? And we need to get y out of the denominator. So we already said to cancel out a rational, you have to multiply, right? So I'm going to multiply both sides by y. These are going to cancel, and I'm left with y times x equals negative 5. So y is not by itself. So what am I going to do with this x? I'm going to divide. OMG. What happened? What happened, y'all? I came back to myself. So the inverse of this rational is it. So. Okay, so how do we feel about writing the equation for the inverse? Doable? All right, let's talk about graphing. So verifying inverses graphically. So there are 2 ways to determine if 2 functions are inverses of each other, graphically and algebraically. Today, we will focus on graphically. On Friday, we're going to focus on algebraically, okay? So today, tomorrow is graphically. Friday will be algebraically. Well, not quite Friday. We got to learn a skill first before, but we're going to get there. So when you have a graph, and you're trying to verify inverse, we talked about it yesterday. You have your line of reflection. So this dotted line, this is my y equals x line. It is my line of reflection. It's called y equals x because it's the line where you're at 1 equals 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. You know what I'm saying? So that's why it's called the y equals x line. Okay? If 2 graphs are inverses of each other, they will be evenly reflected over the y equals x line. So if we look here, let's call this, I think I called it, G of x on top. So we have G of x here, we have f of x here, and looking at these two graphs, they are symmetrical with y equals x, right? So that means that they are inverses of each other. So G of x and f of x are inverses. And you proved it graphically. Does that make sense? So you can look, you can double check. So if I'm here, this one is 2 units to the right, and this one is the opposite of it, 2 units down. This point is 1, 2, 3, 4, 5, 2 units to the right. The next one is 1, 2, 3, 4, 5, 5 units down. And double, you're just like, I don't know really. They may not be that symmetrical. 1, 2, 3, 4. 1, 2, 3, 4. Okay, maybe they are. That's it for graphically. If they are evenly reflected over the y equals x, then they are inverses. Book, how do you feel? All right, so let's actually put it to the test. So the question is asking you, are f of x and g of x inverses of each other? And so we're going to prove graphically whether they are inverses of each other. So the first thing we got to make sure we're comfortable with doing is graphing the linear equation. So when you graph a linear equation, you need to know 2 things, right? The slope and the y-intercept. So my y-intercept is my starting point. So I'm starting at 0, 2. My slope, remember that's my rise over run. So from 0, 2, I'm going to rise 1 and run 3. Agreed? So I'm going to go to 0, 2. And from 0, 2, I'm going to rise 1 and over 3. 1, 2, 3. I'm going to do the reverse action. I'm going to fall 1 and go over 1, 2, 3. I'll call it fall and crawl. For me, I need more points so I can try my very best to draw a straight line. So I'm going to make some more points. All right, that should be enough points, y'all, for me to connect and make a straight line. Wish me luck. Now, don't judge me if I don't make it. I didn't make it. I'm not making it. I did my very best. I wonder if I can determine to make. Okay. I tried, y'all. There's my line. It's gonna get there. All right. So I'm going to do the same thing with G that I did with f of x. So again, looking at what I have, this time I'm starting at 0, -2. I have my rise over run, and that equals rise 3, run 1. Agreed? So I'm going to start at 0, -2. We're at 0, -2. And I'm going to rise 3, run 1. 1, 2, 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 3, run 1. Okay. And I'm going to do it reverse. 1, 2, 3, run 1. 1, 2, 3, run 1. And then I'll do my very best to connect again. Here we go. Concentrate, concentrate, concentrate. We're going, we're going. Good enough. I think I did. Okay. Okay. We're going to call it a day. All right. Now, test comes from your line of reflection. So I'm going to graph my line of reflection, which is the y equals x, and see if they are symmetrical with one another. So line of reflection is based off your values or y equals x. And I'm going to just dot it out instead of Are they symmetrical amongst that line? No, right? They are not. Not inverses. And there, graphically proving that they're not inverses. All right, any questions about graphically proving? All right, cool. So we're going to talk about what's called a one-to-one function, okay? So you know that we have a function, and a function has the domain values do not repeat, correct? Now, if it's a one-to-one function, what happens here is that the domain values and the range values do not repeat. So if the domain values and the range values do not repeat, then that means that there is an inverse function for that function. Okay, so a one-to-one function for f has an inverse automatically. So if you can prove that it's one-to-one, then the inverse is a function. If the function is not one-to-one, then the inverse is not a function. Okay, now another way to visually tell that something is one-to-one, what that means also is that it passes the vertical line test and it's going to pass vertical line test and it passes the horizontal line test. So graphically, if the function passes both tests, then therefore it is one-to-one. So that means none of your x's repeat and none of your y's. So if you go back and think about your do now that you did today, you could have decided whether the inverse was a function just by looking at the y values, right? So if I looked at only my y values to double check if they weren't repeating, then I would know that my inverse is a function. If my y values also repeated, then my inverse is not going to be a function. Okay. So what are the graphs of f of x squared and its inverse plus or minus square root of x? So we're going to create the graphs here. I need this to hide because it gets in the way. So we're going to create the graphs. We're going to use our x values. We have 0, -1, -2, -3, 1, 2, and 3. F of x is x squared. So all I'm doing is squaring each one of these, right? Because f of x is x squared. What is -3 squared? -3 squared is 9. -2 squared is -1 squared is 1, 0. And then it's going to be the same for the positive. A negative times a negative is a positive. Okay, so those are the values for that. So I'm going to create that graph really quick here. So we have 0, 1, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to mimic it over here. 1, 4, 9. Because that's the best quadratic you've ever seen. All right, so the quadratic's done. Now we're going to do its inverse. I'll do it in blue. Its inverse equals plus or minus the square root of x. Now, what's the square root of -3? Is that going to work for us? It's really not. But what we're going to talk about here is that the negative is going to be NA, right? NA, NA, And now I'm at 0. Well, the square root of 0 is 0. 1 is not, none of these are going to help for us as a perfect square. So what I'm going to tell you to do is we're going to use different values for here than these x values. I should make 2 x charts, but I didn't. So we're going to let x be something else. So if we let x equal 4, and we plug it in, what's the square root of 4? 2. So our y is actually going to equal, notice that plus or minus? Our y is going to equal plus or minus 2. That's a positive 2 and a negative 2. If we let x equal 9, what's the square root of 9? 3. So we're going to have a plus or minus 3. And now we're going to graph. I would say the next one would be 16, but we don't have enough to do 16, so we'll just do it again. So we're going to go to 4. So we have 0, 0. We're going to go to 4, 1, 2, 3, 4. And we're going to go up 2. And we're going to go down 2. Because it says plus 4, minus. And we're going to go to 9, 4, 5, 6, 7, 8, 9. We're going to go up 3, 1, 2, 3. And we're going to go down 3, 1, 2, 3. There are my points, and I want to connect them. Okay. So to test the symmetry, remember, they need to be symmetrical along the what line again? So y equals x line, right? So here's my y equals x line. Oh, I can draw y'all. My dots and I are not being friends. There it is. There's my y equals x line. I have 2 rando dots there. And they are symmetrical. Next week, we will talk about why, yes, they are inverses graphically, but is the inverse here a function? Is the inverse a function? No, it is not. And that's because it fails the vertical line test. And that tells us that the quadratic function is not 1-to-1. All right, have a great day. Thank you for a great morning.